2 videos ago, we kept saying the same thing. Km, not Ke, not Kt, is the number that actually tells you which motor design is more efficient. Today, we open that claim up properly. Formally, Km is defined as torque, divided by the square root of I squared R, the copper loss. In plain terms, it measures how much torque you get per unit of heat you're willing to dissipate in the windings. And here's the property that makes it so trustworthy. It's Co. For a fully realistic motor, Km is too complicated to solve with a clean formula. There are too many interacting geometric factors. But for an idealized case, full pitch windings, 1 slot per pole per phase, an exact relationship does exist, and it reveals which levers actually matter. The first and strongest lever is air gap flux density, Bg. Increasing Bg is the single most direct way to raise Km, because it feeds straight into the torque in the numerator, while only weakly increasing resistance in the denominator. Stronger magnets let the teeth and yoke stay slimmer, so the trade-off tilts heavily in Km's favor. As a result, motor constant increases nearly linearly with air gap flux density. The second lever is rotor radius, and here the answer genuinely depends on what you hold fixed. If the stator outside diameter is allowed to grow along with the rotor, Km increases linearly with rotor radius, straightforward. But in practice, the stator outside diameter is usually the fixed constraint. It's the physical envelope you're designing into. Under that constraint, growing the rotor radius eats directly into the slot area available for copper, so the benefit is weak. Practical experience across real designs has shown the optimum rotor radius typically sits between 40 and 65% of the stator outside radius, that gold band you see in the diagram. That rotor radius trade-off leads directly to a real design fork: the copper motor versus the magnet motor. Both cross-sections here have exactly the same stator outside diameter, the same envelope, but they spend that radius completely differently. The copper motor keeps the rotor smaller, leaving more room in the slots for winding less magnet material. The magnet motor does the opposite: a larger rotor radius, more magnet material, but less room for copper. Neither philosophy is wrong. They're two different ways of allocating the same physical radius, and Km is precisely the metric that lets you judge which allocation actually wins for a given design goal. The third lever is pole count. Km grows with the square root of the number of magnet poles, and slightly faster than that in practice, because adding poles also shrinks the stator yoke width, freeing a bit more slot area for copper along the way. And let's close the loop on what does not move Km: winding turns. More turns raises Kt, but cuts the achievable current by exactly the same factor, so Km, built from that ratio, stays completely put. That's exactly why it's the trustworthy metric for comparing motors. So, 3 real levers. Air gap flux density is the strongest and most direct. Rotor radius is real, but secondary, tightly coupled to your fixed stator envelope. And pole count gives a modest faster than square root gain. Master those 3, and you're actually designing for motor constant, not just measuring it.